All righty. Welcome back, everybody. So today I'd like to pick up where we left off last time. Shh, settle down. I realize that it's sunny out for a change, which is kind of nice. But if you remember from last time, we started talking about data structures for translating addresses from virtual space to real space. And we talked about very simple paging as a starting idea, where there's a page table pointer that points at a page table. Typically, there's one page table per process. And the translation is very simple. To go from a virtual address to a physical address, you first copy the offset. And this offset, of course, as we mentioned, is related to the size of the page. So, for instance, if it's a 4K page, this is 12 bits. If it's a 1024 byte page, it's 10 bits. You copy it directly, and then you take the virtual page number, you index into the table, you look up the physical page number, copy it in, and you're good to go. All right? And I'm assuming you guys can all do subtractions, right? So, for instance, in the example down here, we have 1K pages, meaning 10-bit offset, which leaves 32 minus 10 equal 22 bits. So there are a total of 4 million entries in that page table. Okay? And so the problem with this scheme, of course, is we really actually want to have a lot of holes in this table. All right? The other thing, just to get sparseness, the other thing that's want to mention here is, of course, the page table has some finite size. And so typically we take the virtual page number and check against some size in this scheme. And also there's some access permissions, which we also check against. So if you look on the right there of that blue page table entry, we say that the page is both valid and read-only. That's what the R means. If the process tried to write, then you'd get an error. Okay? Any questions on this? Notice also, by the way, this N is a good example of a page that doesn't exist at all. So if the virtual page number happens to be equal to 4 and you try this, you get an access permissions error no matter what. Okay. So what do you need to switch when you context switch? Well, the page table pointer and the limit. So if you look here, this is very simple. Just by switching these two things, suddenly we have a completely different address space. Okay? So the pros of this scheme is very simple. It's easy to share. We'll mention sharing again. Cons is if the address space is sparse. And, of course, we talked a lot about sparse address spaces. Why? Stack grows down, heap grows up. Big hole in the middle. That's a great example of sparse. Okay? If the table's really big, we'll also look at this in a little bit. But imagine a 64-bit address space. How many entries are there? Many. Okay? So, at the end of the lecture last time, we were kind of looking at multi-level ways of kind of addressing this. Here's a thing to remember. So this is an example of what the 32-bit address space for Linux looked like, free time to deal with Meltdown. But what's interesting about this is the stack. There's a big space in here for the stack to grow down. There's a big space for memory mapping segments for shared memory to grow down. Big space for the heap to grow up. There's also random offsets in there to try to defeat different attempts to break a kernel, so that if somehow you manage to inject some code into this system because of the random offsets, it still might not be properly executable. So that's why there's randomness in there. Okay. So how did we, right at the very end, we started saying, all right, if we really want a sparse address space, what else could we do? And so that led to the two-level page table that we discussed. And this is what I like to call the sort of perfect page table. It's for 32 bits of address with 4K page sizes. And what's great about that is if your page table entry, which I'll show you in a moment, is 4 bytes, then the top-level page table, if that's exactly one 4K page, that means there's 1,024 entries. So 10 bits is enough for that. You index into there. That gives you the next level page table. That gives you another 10 bits. Okay? And that, when you're done, gives you the physical page. And, of course, you've copied the offset as before. And why is this perfect? Well, because it's 1010 is for 1,000 entries in each of the page levels, and 12-bit offset, 10 plus 10 plus 12 is 32. So it works out perfectly. There's valid bits on both levels. So you put valid bits in here. What that means is if you have an invalid entry at the top level page table, then any attempt to have any address that the top 10 bits matches to a page table entry with invalid means you get a page fault. Okay, why is that kind of a cool? There's at least two reasons why that's kind of cool. Anybody have a thought? Why is it interesting to be able to have invalid first level page table entry? Yeah. Great. So in the sparse case, one invalid bit at the top level equals 1,024 invalid bits at the next level. So that's great. What's another good reason for doing this? I mentioned it briefly last time, so if anybody remembers. I'll give you a hint. Just because it's invalid at the top level doesn't mean that the page table it represents is invalid at that point. Yeah. Well, sharing is also going to be something we talk about, but not. This is not after sharing. Yeah. Yes. Perfect. So I could page this level out to disk, mark this as invalid, and now I can have most of the second level page table out on disk, freeing up memory. And so if I happen to try to access it, what happens is the page table hardware will cause a page fault at first level. The operating system will say, well, it's a page fault, but it's actually valid. Pull it in off disk, make it valid, and then retry the access, and now you get the second level works out. So you can actually page out part of the page table as well. Keep in mind, by the way, and this is an exercise to the listener, you can't really page out the top level. Okay? If that process is runnable, the top level has to exist. Okay. Now again, to page out or to switch context from one process to the next, we just change the page table pointer. Okay. Now I know there was a question that popped up on Piazza about what's in that 4 bytes. I'm going to tell you in the very next slide. But before we get there, are there any questions about this? Yeah. So waste space relative to the original idea of a million entries in a row? Well, it's a little bit. If you had 100% of your pages were allocated, this page table will take a tiny bit more space than the other one, but it's not going to be much. In fact, the only difference between 2-level and 1-level, if you really had 100% of your pages allocated, is this top level one is wasted, which is 4K bytes, which really doesn't mean anything in a 4 gigabyte RAM space. The flexibility you get for not dealing with sparseness, or for efficiently dealing with sparseness, way outweighs that tiny little loss of a page. Good question. Okay? Any other questions? So, all right, so this thing here, each of these entries is called a page table entry. And technically speaking, this is a first level page table, second level page table, but Intel often calls that first one a directory. So the first one they call a directory, and the second one they call a page table, whatever. That's their terminology. But these are all page table entries here, and they're 4 bytes in this simple case. And what's there? Well, clearly we need a pointer to the next level. So if you look at this, obviously there's a pointer that points us to the next level page table. How many bits is that? How many bits is a pointer to the next level page table? And actually, you could start by asking how many bits is this guy? They're the same. How many people think it's 32 bits? Okay. Probably not, because there's an offset that's 12 bits. So what might be the next obvious option? 20 bits, right? So if you were to ask in my 32 bits of address space, 20 bits to find which page it is. And so each of these guys is 20 bits long. This is 20 bits in here, and there's 20 bits of this 4 bytes is a pointer to the next level. And notice, when we fill in this physical page, how many bits is that? Well, it's got to be 20 because it's whatever isn't the offset. So those 20 bits also come out of here. So this guy's got 20 bits, this guy's got 20 bits, this guy's got 20 bits. Okay? And so if you look at a page table entry, here's an example of the x86 entry, and yes, indeed, 20 bits are what are called a physical page number or a page frame number. What about the rest of them? Well, the most important one down here at 0 is the equivalent of the valid bit, although it's called present on Intel architectures. Okay? And then these other ones are interesting. So the W says whether this page is writable or not. U says whether the user can access or only the kernel. And then there's a couple of things that talk about how the cache works there. So the cache is the hardware cache on the processor. So you could say, never cache anything on this page or always write through, etc. The other is whether the page has been touched or not. So that A bit's going to get really interesting when we start talking about things like the clock algorithm for paging, okay? But what that A bit means is if your program has touched that page in any way, that A bit gets turned on. And then finally, a D bit is if you've written the page. Both A and D are part of the clock algorithm. And then L is a special thing that says whether at the top level, whether there is a next level of page table or whether you're pointing at 4 megabyte pages or not. So those are super pages in some instances. Okay? And that might be for the kernel or something where you're not going to be paging in and out a lot. Okay, questions? So the format of this page table entry is the same at both levels. And, you can have something be present, you can have something be writable, indicate whether it's writable or not at this level as well. Okay. Now, what can we do with this page table entry? So, an invalid page table entry can mean several different things. First of all, it just says that the region of the address space is actually invalid. Typically, you end up with a segmentation fault if that's true. Another thing could mean the page is out on disk. So that's a page fault where you start scheduling the page to come in off of disk. You put the process to sleep on the disk's wait queue. And later when that page comes in, you clean everything up. You make that entry valid or present instead of not present. And you continue. Now what's interesting also is the present bit is checked first. And so if this P bit is 0, the other 31 are free. So sometimes operating systems will put extra information in those original 32 bits the first 32 bits if the 0 bit says not present. And what you might do with that is where on disk is this page, for instance. Okay. All right. Now, some other examples that we can do. So for instance, demand paging is what I just told you about, and we're going to talk more about. That's kind of one of our next topics after we talk about caching again for a little bit. But the idea of demand paging is only the active pages of a process are in memory. The rest of them get pushed out to disk. And so that present bit can be used to decide whether the thing is actually in memory out on disk. And a paging algorithm, like the clock algorithm, can be used to essentially push the unused pages out on disk. So the only thing you actually have to have in memory are the ones that are actively in use. And what's kind of nice about this, I'm going to remind you guys about the segmentation versions that we showed first with just the bound and base version that we showed you about. That you had to put the whole segment out. This now you can just put out a page at a time or not, depending on which pages are active. So that's pretty cool. Another one, which we talked about when we first introduced fork. I know this is now getting way long ago, like a month or two. Was copy on write. So if you remember, when you do fork, what happens? You get a full copy of the address space. Well, you don't copy all of the data. That would take too long. Instead, you essentially mark all the page entries of both the parent and the child as read-only. And then if either of them tries to write to a page, you check and you say, well, is it actually writable or not? And if it's actually writable, that's the point at which you make a copy. So you only make a copy when you need to. Okay, and why can the operating system do that? Well, because we start by marking this thing as not writable. And then when you go to write it, the operating system gets pulled in as a page fault, and you clean up the parent or the child, whichever one tried to do the write, by making a copy. Okay? And then finally, there's a zero fill on demand is used a lot too, which is I got a chunk of memory and I want to make sure that I don't leak information to a process. So I want to make sure that the pages that I give to a process when it does sbreak move, which is effectively malloc, are zeroed. Well, why waste the time to zero everything out until you actually need to? And so here, again, I can mark pages as, say, read-only or even invalid, actually in this case invalid. The moment they try to read them, then I'll zero them out and make them valid again. Okay, so I don't even go to the trouble of zeroing things out until they're something that's actually in use. Okay, questions on these three things? Yeah.
So, in the example use of the copy on write when we import, we do make a copy of the parent's page table, but then they point to the same page.
Yep.
Point to the same memory, but
Exactly.
But that doesn't make it so that they can share.
No.
Memory.
Well, we make a copy of the page table, so that's just the thing in the middle. We mark everything as read-only, and it still points to the same physical pages. So yes, they're sharing, but they're only sharing a copy of the pages, which of course they were going to have anyway. The moment they try to write, then you get a page fault because it was marked read-only, and then you split it into two pieces. So again, you're not sharing because the moment the parent or the child writes, you get now two copies and their writes go into their own page at that point. And so yes, they're initially sharing the same read-only copy of the physical pages, but there's never any sharing of information back and forth other than that initial sharing that happened at fork time.
This is the pages like not in the middle, but all the way to the right.
Yep. So these are the real pages here. These are the ones that you get when you read and write. And so these are shared. These are copied. Initially, both of them are identical copies of each other, all marked as read-only. And then as soon as one or the other tries to write their page table, write, say, some page here, at that point, we make a copy of this page. We clean up two page tables to point to different actual physical memory. Good. Okay. Any other questions? Yeah. Well, it's a page fault because the page is marked as non-writable in that case. And so that, because it's marked non-writable and the process tries to do a write, you get a page fault. Well, in this instance, the user wouldn't see that page fault. What would happen is the operating system would take over and make the copy, and then it'd restart the user program to try the write again, and it worked the second time through. So that's a great question. How does the operating system know that this is a valid write as opposed to an invalid write? And the answer is there's a few free bits in the page table entry. The operating system can write a couple of bits in there to say what's going on. Yeah. And if that doesn't work, you guys are all clever, right? You're here at Berkeley. If that doesn't work, then you could always have your own shadow information somewhere that says for this given page in this process it's writable or whatever. Yeah. But oftentimes there are a few spare bits in the page table entry that are actually left for operating system use. Good. Any other questions? Okay, good. All righty. So summary of two-level paging is basically that there are two levels, page 1, page 2. For instance, if we're trying to translate this heap address, notice we split off the first and second indexes. The first one goes to the first level page table, which gives us a pointer to the second one, which goes and points at the final page, and we're good to go. The important thing to keep in mind about this is in the best case here, the total size of the page table itself is roughly equal to the number of pages used by the program in virtual memory. Okay? Because if you think about that, there needs to be enough page table entries to point to the parts of virtual memory that are in use. Okay? that's not necessarily related to the total number of pages that are actually in memory, because a lot of them might be out on disk. So when we, toward the end, in a few slides, we'll talk about a solution to that. But this one has a page table size that's roughly related to the amount of address space in use in the virtual side. Okay. So then we talked about trees of tables. So lowest level page table being equal size blocks. You can still use a bitmap. Higher levels could be segmented, could have many levels. So for instance, here's an example. Mix it up, right? So here we've got a couple of bits for the segment ID and then a virtual page ID. And we copy the offset. And so we could take the segment ID. That gives us a base, not of the segment this time, but of the page table associated with the segment. And then we can look things up to get the physical page. Okay? And then we can check access errors and permissions and so on. Okay? And typically, this is definitely a segmentation fault here if there's not a valid segment. This is could either be a page fault that the operating system cleans up, and sometimes you'll get a segmentation fault if ultimately the operating system decides not to clean it up. Must be saved and restored on a context switch. Okay, this is a question you know you're going to get asked sometime, right? So I will tell you now that the segment descriptors are often somehow in the processor, as is the point of the page table. So in this case, we're probably saving the segment descriptor, right? In the previous example here, you could say probably the page table pointer is the thing in the processor you're saving. Okay? So just trying to keep in mind what it is you're swapping out. All right. Sorry for going back and forth here, but these are a little bit intricate. Okay, so what else could we do? What about sharing? Okay, people brought sharing up, so we can now share a complete segment, right? So here, process A has a page table that's a segment. Process B could point at the same segment. Voila. Now we're just sharing a complete segment. So now in this case, we could have a data segment that's shared between two processes that are used to communicate with each other. Okay? Clear to everybody? Not too complicated. Notice we could actually mark one of these as invalid if we wanted to. There's a lot of options of other things we could do. We could have sharing at the page level and have one process be able to read and write a page while the other one can only read. So there's a lot of opportunity here for sharing at different levels. Yeah?
So would this be like something that's like copy when you make a new thread? Like you're copying this segment?
No, this is, because we're talking about slightly different segment tables, we are still talking about different processes. So this would be sharing between processes. Threads always have the same page table, and so threads within a process have the same page table, so they just share because they're in the same process. Everybody catch that difference? Yeah, question? So the difference here is that each one of these segments can point to a page table that's in potentially variable size, whereas the previous multi-level page table I showed you, both at the first and the second level were exactly a page in size. Okay? So what I'm trying to show you is a lot of, and you can know that, by the way, by the fact that there's a base and limit here that could get checked. I'm showing you some options just so you guys don't get stuck in your mind on particular versions, because there's lots of different options out there. Okay, I just wanted to show you. In fact, in the moment, I'm going to show you what actually happens on an x86. So here's the multi-level. The pros are we only need to allocate as many page table entries as we need for the application. The memory allocation it's still pages. The share is easy because we can share at the segment or the page level. Cons are typically you have a pointer per page, which when we get to a 64-bit address space is very problematic. Page tables themselves typically need to be contiguous. So if you looked at the two-level page table, each level was completely contiguous. It was one 4K block and a bunch of sub-4K blocks, each of which was contiguous. If you had the continuous one-level page table, that's much bigger contiguous, much worse. And the other thing which hopefully is starting to bother a few of you is that to do a load or store, we got to traverse a page table. To do a load, we have to look up something and then look up something, and then we can do the load. So a load, which might be an expensive operation, suddenly comes into 3 loads. Or in the case of a big 48-bit virtual address space, in some instances it might be 4 loads, or it might be 8 loads in the case of a shadow page table support for virtual machines. So somehow this seems great until you start thinking about what we're asking the processor to do. We're asking it to reference on an already slow operation. So hopefully that's starting to bother people. What's the answer going to be? Caching. Okay, and there's a special type of cache called a TLB. Very good. We'll get to that in a second. So final Project 1 report's due today. Project 2 release is on Pi Day. So happy almost Pi Day. All right. I strongly support at least 1 point dancing in a circle and reciting as many digits of pi as you can, because this is important to do on Pi Day. Everybody should wear their Happy Pi Day T-shirts. All right. Maybe I'll have to actually pull up the. There's a Pi Day song that's pretty good. That's to the tune of the American Pie song, American Pie, but it's actually American PI song. It's great. So, midterm 2 is on Thursday after spring break, just so you know. Okay. So I wanted to briefly say something here. I saw a note on Piazza. Every now and then I'd like to comment on notes. So, those of you who looked at the solutions for 3C from the exam probably said, oh, that doesn't protect against freeing twice in a row. Okay, how many people sort of had that worry? Anybody? There are a few of them. That's okay. I wanted to point out that, technically speaking, that's a misdirected worry. Okay, because you could fix the solution in 3C so that if you try to free a freed lock, it doesn't do anything bad. You could do that. But that's actually not really helpful. A better enhancement would be if you ever try to free a free lock, it crashes the program with an error. That would be a much better solution to freeing a free lock, not transparently making it work. Okay, and the reason is, the reason I wanted to say this is I want to make sure you guys learn a few important rules about locking. One of them is always have to match a lock and a release together. Always. Okay, because if your thread could do 2 frees in a row, that means that under different circumstances, it could free a lock that it doesn't possess, but that somebody else grabbed, and now you just screwed up your synchronization. I'm going to say that again. The fact that you could free twice under any circumstances means there's an extremely subtle bug in your program that on a different interleaving of threads could free when somebody else has just acquired the lock. And now suddenly you've got very bad synchronization problem because you've just violated their critical section. All right? I just wanted to say that out loud in class to try to get that in your brains. Okay? Freeing a free lock always means something bad. Okay? It means either you got a bug that's about to happen, or you got a bug that happened, and you're going to spend all night debugging it. So always match up acquires and releases. All right. Questions? Okay. Yeah, a good lock package would let you turn on something that gives you an error or an assertion when there's a... Okay, the other thing I wanted to point out is be aware of the collaboration policy. So things that are okay in this class are explaining concepts to somebody, discussing algorithms over coffee, helping maybe to debug somebody else's code a little bit, but not sharing code, not reading code in detail, not copying code online. We actually check for these things, and that makes both of our terms much more unpleasant and complicated if we discover copied code, so just say no. All right? Just say no. Did I just say no? Just say no. Do not. This is not the class you were taking. Okay. All right. So let's make this real for a sec. The x86 memory model with segmentation, as long as you don't do the 64-bit versions, which kind of do something different, looks like this. So you actually start with a load, store, whatever your memory operation is, and attached to it is a segment descriptor that says, do this with a particular segment, okay, the CS segment or the ES segment. And what happens is, out of your address, they pull off the offset, and the segment selector is part of the instruction, so the offset's really the address itself. That segment selector looks up in a table, which is either the local descriptor table, LDT, or the global descriptor table, GDT, which pulls out a segment descriptor, which has a base, okay, and a size, which is then combined with the offset to make a 32-bit address, which is now a flat, what we call a flat address. It's in the 32-bit address space. So you start by saying, here's a segment, the base address plus my limit offset puts an address in that main space, and then I go to a two-level page table, just like we talked about before, where the first level is typically called the directory and the second is called table entry, but this is just two levels of page table and a lookup. And so this is how segmentation and paging is combined together. The segment gives you a chunk in the linear address space, and then the linear address space is paged in normal fashion. Okay? Now this global descriptor table is actually in memory. The segment selectors are in the processor. So the segment selector goes and pulls out, it's a 13-bit segment descriptor number. It pulls it out of the segment descriptor table, which actually points to real memory. So this is even more complicated descriptors than I told you before, but it's roughly the idea that you have segmentation, which is then on top of a linear address space. Yeah. Yeah, it's different from this previous slide. You don't mean this previous slide. You mean this one? Different than this one? So the way this is actually, the way the x86 one is different is you first take your offset in your segment and add it to the base, and that gives you an address, which then you feed to a two-level page table, which is different from what I've got here. So the segment has a base and a length, and your offset inside that base and length then gives you an address, which is a 32-bit address that then fits in the linear space and is paged normally. So one thing you can do, what a lot of operating systems do, by the way, is if they don't want to use segments at all, they make every segment selector has a base of 0 and a length of 2 to the 32nd, or 2 to the 31st, okay, minus 1. So 2 to the 32nd minus 1, so that the segments are complete size of the address space, and so then segments really don't mean anything. That's what a lot of operating systems like Linux do. If you want to go back to the segment model, you can actually have segments that have a more restricted size in them. So, yeah. So why do you need segments at all? Well, the original 16-bit versions of the x86 actually had segments that were used a lot to say what's the stack and what's, they actually use segments fundamentally as part of the model. As the processor has evolved over time, there's a lot more sort of linear address space that's used. Okay, but I will tell you that there are two segments like the ES and the FS segments are still used a lot, even in modern operating systems. In Linux, for instance, they're used for the thread local storage. So what a thread has is every thread has storage associated only with that thread, and that thread local storage is pointed at by the ES and FS registers. Anyway, more details than you need to know, but I thought I'd point it out. So I thought I'd point out what the segment selectors. So in the processor, the segments look like this. So if you say, what is SS, CS, DS, ES, FS, GS? Oh, by the way, I meant FS and GS are the ones you can use today. But if you look at in here, the segment registers in the processor actually select the segment and say whether it's the GDT or LDT and also what level of protection that segment has. And then the segments look like this. These are the descriptors. And what's funny about this is not for you to know every little bit, but I want you to focus for a moment on that mustard yellow, because this is the base address of the segment. And if you notice, in the original days of 16-bit processor, of the 8-bit x86, there was sort of the base address was 8 bits down here, and then it went to larger, the base address got bigger, and then they had a little bit more, so they went from 16-bit descriptor to 32-bit descriptor to 64-bit descriptor. And so this is what happens when you try to keep everything backward compatible. It's really messy, right? It's actually kind of funny in the grand scheme of things. But all right. Any questions? Anybody ever have to deal with this before? Probably not too much. Unless you're writing a compiler, probably not. Okay, so there's a set of global segments for everybody, set of local segments for every process. In legacy applications, the segments are used a lot. In 32-bit mode flattened, typically GS and FS are thread local storage. And the way that you use thread local storage, even in modern C compilers on top of Linux, is like this, where you move a value into GS of 0, says the thread local storage, the first word of the thread local storage is that, GS of 0. And every thread has thread local storage. So when we context switch between threads, we actually swap out the segment descriptors. And so there is a little bit of storage dedicated to each thread. It's not protected from the threads in the process, but it is independently addressable, which is useful for certain variables and stack information, and so on. Modern use in the 64-bit long mode is the segments are actually just disabled in the processor. So they all have 0 offset and no length limit, and only FS and GS even retain their functionality. So by the time they got to 64 bits, they sort of are throwing away segments because they pretty much aren't used. So, all right. That's enough of reality for you guys. Let's go back to something like this. Unless there was a question on reality. Yeah.
Right. So you mentioned this thread local storage is going to save segments.
No, the thread local storage means that every thread in a process has a little bit of storage that's uniquely associated with that thread and that's addressable by doing things like using the GS segment as a segment to offset into it. Yeah. It's used for different things that you might want the thread only to have that's unique to that thread. Could be other pieces of information. It could be data structures. There's lots of ways that that's used. So let's go back to this. So 64-bit processors typically don't have the ability to deal with all 2 to the 64 bit addresses. In fact, they typically have a subset. So here's an example of the 48-bit subset of the virtual address space. The top bits are mostly ignored in that or mirrored in a way we could talk about it some other time. But notice how it's 9-bit, 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 and 12-bit. So that's a 4K pages again. And what happens is that leads to a 2-level page table, or a 4-level page table, which ultimately points at the pages. Okay, and so this is an actual scheme that's used in the x86 processors when you have the large amounts of address bits. Okay? And notice that the page table entries are bigger than 4 bits now, okay? 4 bytes, I mean. The other thing is, you might say, well, what about 64-bit addresses? So now we got a 6-level page table. This is seeming a little crazy, and this is getting ridiculous, right? And so, in fact, the IA64 was one of the first to do the following. There's a few others that do that, and it's called an inverted page table, where what we've been talking about is a forward page table, where you take the address, you split it up, and you index into a tree, and you find the final table entry. So in the inverted page table, what happens is you take the virtual address, you hash it, and that tells you what the physical looks like. Okay, so And this is done in hardware. So you actually take the virtual page address, you go through a hash table, and it pulls out the physical page. Okay? And PowerPC, UltraSpark, IA64, there's a number of processors out there that did this all natively. Okay? AS400 from IBM was another one. And the advantage of this complexity is really that the size is now independent of the size of the virtual address space, but rather related directly to the number of physical pages that a process has. Okay, so the size of the page table is now more related to the DRAM size rather than the virtual address space size, and so that's kind of a nice advantage. So, cons here, of course, is you're managing hash chains in hardware. And another con, which is really a big deal these days as well, is you get very poor cache locality, because if you think about pages that happen to be close to each other in virtual space are spread all over the place because of the hash chains and probably don't hit the cache very well. So inverted page tables have a little bit fallen out of favor these days. Okay, questions? Except that they're still in use with some of these processors. So, okay? All right, so this is total size related number of pages used by the program in physical memory. All right. So here's a comparison of what we talked about. We had simple segmentation, which is very fast context switching. Segment mappings maintained by the CPU, but you get fragmentation because all the segments are different sizes. We talked about simple paging, where there's no fragmentation externally because the pages are all the same size. The allocation's easy, but now you got a really large page table size, and it doesn't deal with sparseness very well. We talked about a couple of multi-level options where the table size is more closely related to the amount of virtual memory in use, and but now we got many memory references at a time. And then finally, we just talked about the inverted page table, where the table size is more related to the amount of physical memory in use, but then the hash functions are in hardware, and you got poor cache locality. So I think that kind of covers them all. All right? Good. Yeah. I'm not sure I understand. So when you have multiple processes, every one of the page tables are in memory at the same time. Oh, I see. I see. Yeah, that's a good question. So in fact, between the world of 32 bits and the world of 64 bits, there was this transition period where people started putting a lot of physical memory on the system, but mostly there were still 32-bit processes. And so there is a mode in the x86 that lets you say that the processes are 32-bit of virtual address space, but it can address more than 32 bits of physical space, which is kind of what you just said there. And that is a mode. That's a mode in control registers that you can do. And so that way you can support a lot of 32-bit address space things running together at the same time with a lot of DRAM. And that kind of mode showed up right after 4 gigabytes of real memory started becoming not enough, and before 64 really took over as a size. Yes. Okay. So, how is this translation is there another question? I'm sorry. Everybody good? So, how do we actually accomplish this translation? Well, very simply, the CPU produces virtual addresses, something's in the middle, and you get physical addresses. Okay? So something in the middle is an MMU often, memory management unit. What exactly happens inside there? Well, one option, which is quite common, is you actually have hardware that traverses the page table. So all that has to happen is you set up the base of the page table and maybe segment registers in some instances in the MMU, and virtual addresses come in, and what happens is the MMU does all the work of looking things up in the page table for you to produce a physical address. okay, and it generates a page fault if it ever encounters a page table entry that's invalid. And so that's, this MMU is closely associated with the CPU. It used to be a separate chip, but today it's always in the same, right next to the CPU. And the pros of this scheme is it's pretty fast because hardware is doing it, but it's inflexible because you can't change the page table structure really. And the hardware is kind of complicated. Now, that's less of a worry these days when there's so many transistors out there that anything you can do with transistors might be worthwhile. The MMU is a good example where you really do want to have that lookup as quickly as possible, even when you're caching. We'll talk more about that in a moment. Another possibility is software tree traversal. So in the old days, not that long ago, when in the previous iteration of this class, we actually had you doing an operating system on a version of a processor that was like a MIPS processor. And the thing about MIPS is MIPS doesn't have a hardware page table walker. What happens is when the TLB, which is a cache on addresses, faults because there's something isn't in the TLB, you actually get a TLB fault. And software takes over, and the software in the kernel walks the page table and either installs an entry back into the TLB or later, or if it finds an invalid page table entry, it'll give you a page fault at that point by calling the page fault handler. Either case, however, either traversing in hardware or certainly in software is much slower than you want, so we really need a cache on top of this somehow. Okay, something to cache that translation between virtual and physical so that we can make it fast. And that's kind of going to be our next major topic. And before we do that, let's take a brief break now, and we'll come back and continue. So we had a couple of questions afterwards, one of which I wanted to mention here. When you think about what we're doing with these various mappings, we are mapping from the virtual space to the physical space. And the question that could come up is, how do you decide what physical page gets mapped to a particular part of the virtual space, right? You could wonder that. And what you should know at this stage, we'll get into paging as our next topic after we remind you about caching, is this is any page can be, any physical page can substitute in for any virtual page, because we have made a mapping here that's capable of any to any. So the interesting question is going to be, how do you make those decisions, and how do you decide which physical pages are no longer in use, and so on? And that's when we get into paging. That's part of the paging algorithms that are going to be our next major topic. Okay? So this is a fully associative mapping from virtual to physical, and keep that in your brain for later. Okay, so before we do that, I want you to recall something we talked about at the beginning of the term, which is this notion of dual mode operation. So can a process modify its own tables? No, because that would defeat the whole purpose, right? We do not want a process to be able to reach in and change its page table, because if it could get access to physical memory, and we no longer have any protection. We might still have translation, which could be useful, but we won't have any protection. And so we have to restrict it somehow. And of course, we talked about dual mode operation, first day or second lecture, whatever, where the hardware has at least two modes, kernel mode and user mode. And the mode is set in bits in a control register, but only the kernel can actually set the bits. The user has to get into kernel mode in some way, like a fault of some sort. We'll talk about that in a second. And the kernel, of course, can easily switch back to user mode just by changing the bits to user mode. Okay? Now, I also mentioned, this is a curiosity for you guys at parties, right? You're always looking for good things to talk about at parties. The x86, I'm sure you guys are always looking for things to talk about at a party, actually has 4 protection modes since the beginning of time, because it was built after the military spec with 4 levels of protection. They're called rings, and most operating systems only use 2 of them. So ring 0 is the highest privilege, that's typically kernel mode. Ring 3 is user mode. Rings 1 and 2 are not often used. Okay, there are some instances where they're used. And newer processors additionally have a mode which is called hypervisor mode, or ring -1, which is higher privilege than the operating system. Why? Well, because the hypervisor allows you to have many operating systems running in virtual machines at the same time. Okay, and so the way that they got that to work was, amusingly enough, you could say, well, before the ring -1 became in fashion, they actually used 3 of the rings. So ring 1 was kernel mode, ring 3 was user mode, and ring 0 was the hypervisor. And they did that for a few things, like Zen is a good example of an operating system that did that. But now they go back to this more normal mode, and ring -1 is for the hypervisor. Obviously, why do any of this? Well, because certain operations are restricted to things like kernel mode, and hypervisor is even more restrictive, but includes modifying the page table. So we make sure that only the kernel can modify the page table. And when you look in the x86 spec, for instance, there's a control register, CR3, which is the base of the page table. Okay? And there's also the base GDT, LDT registers. Those are things that are only modifiable in the kernel. Okay, and that's how we get protection, because only the kernel can install a page table, and you put the page table in kernel space, and so the user can't modify his own page tables and also can't swap in a new page table, and voila, we have protection. Okay? Good? Now, recall, how does the user get into kernel mode? Well, if we're trying to think of this, we can't let the inmate get out of his padded cell on their own. So we have to make sure they go through the door, right? So that's the idea of a system call, okay? How does the user program get back into the kernel? Well, for instance, a system call is a voluntary procedure call into a higher level mode of the kernel, and it's moderated by hardware that makes it controlled. So to go from the user to kernel transition, remember, not every kernel routine can be called, only the ones that are in the system call table. And the system call ID is typically encoded in the system call instruction. Okay, and so we enter into a well-defined gate into the kernel and transition into kernel mode in one atomic operation. And that's what a system call is. And in fact, what are some system calls? If you remember, these are all ones you're all familiar with now, right? Open, close, read, write, fork, exit, etc. What happens at the beginning of the system call? When you enter the kernel, it sets the system to kernel mode and calls a handler in that limited set. And where do the arguments get passed? Well, if you think about it now, we have user writable and readable and modifiable memory, and then we've got kernel memory. If we're passing arguments from the user to the kernel's got to be very careful because you don't trust the user. So what that means is either the user puts them in registers, so there's a limited number of registers that you can use, and in x86 there's a very limited number. You could write into user memory before you make the system call, but the kernel copies, right? The kernel doesn't trust the user's arguments in their own memory. They copy out of memory, but first checking that they're valid addresses. And every argument's explicitly checked. So if the user gives you a pointer, you make sure that the pointer is valid. It's in the user's space. It's accessible by the user. You check, you check, you check again. Okay? So the way the user gets into the kernel is basically what's called an exception, and there's at least two types. I mentioned this once before. I wanted to say it just to make sure we got it back in your brains. Two types, traps and interrupts. Okay, and a system call is an example of a synchronous exception or a trap, often called a software trap instruction. Other synchronous exceptions are things like divide by zero, illegal instruction, bus error, segmentation fault, page fault. These are all synchronous. Why are they synchronous? Because they occur at exactly the same spot in the user's instruction stream, synchronous with a particular instruction that caused the problem. Okay, and you could say that a system call is a problem with user code because it's going from the user code into the kernel. So that's a synchronous exception as well. Interrupts are asynchronous because they come in at a time that's independent of where the user code is running. And so they can interrupt pretty much anywhere. And the examples are timers and disk ready and network. Interrupts can be disabled. Traps cannot. Because if you divide by zero, you got to go into the kernel for it. Okay. Now, oftentimes, if the user wants to disable certain things, they can set a signal handler to null, right? You're aware of that, but that has bounced into the kernel first and then been ignored. And then on a system call, exception or interrupt, the hardware enters kernel mode with interrupts disabled. This is all recall for you guys. Saves the PC, jumps to appropriate handler. Some processors, like the x86, also save registers and change the stack for you. And then the handler does anything else that still needs to be saved. So a lot of processors, other than things like x86, save the registers, switch the stack, etc. Okay. Yes? So, good question. Where is the page table? So first of all, it's definitely going to be in kernel memory. So the user does loads and stores, and the page table gets accessed not by the user, but by the memory management unit that's translating for the user. The user never touches the page table. Okay, now, like everything, there are some qualifications on that because there are some special modes where the user is given control over certain parts of their address space and so on and so forth. But for now, we'll say the user absolutely has no control. Okay? All right, any questions on that? Since I might as well throw out something as an amusing thing to chew on a little bit. Some processors put the page table effectively in the virtual address space of the kernel, and some of them use it only in physical memory, and that depends on the processor. Okay. So how do we get from kernel to user? That's much easier. So we could ask, for instance, what does the kernel do to create a new user process? Allocate and initialize the address space. Read the program off the disk, put it in memory. So what does allocate and initialize the address space mean? Well, it means we're setting up first the control block, and then we build the page table so that it is the user's address space for that process, right? And then we do what we talked about for the thread root, if you remember, but we've allocated address space first, so that's the only real difference here from thread root earlier in the term. We have to set the hardware pointer to the translation table, which is CR3 in the x86, set the process status word for user mode, and then jump to the start of the program. And how does the kernel switch between processes now? Well, the only difference between switching between processes and threads inside the same process is now we might have to change the address space. So we might have to save and restore the hardware pointers to the translation tables and stuff. That's part of switching from one process to another. Okay? Questions? Good. Okay, closing thoughts. So I've been talking about hardware a lot. Can you do protection between user processes without any hardware that does something special? And the answer is yes. So you don't actually have to have hardware support. And you've already experienced some of these. So one is we can have a strong typed language that never allows you to even address the memory of a different process's data structures. Okay? If everybody sticks to the same language and you load programs from that language into an environment that only runs things from that language, in principle you can do that. So things like Lisp and Ada and Java even kind of work that way. Those are virtual machines. The other is you could get even more, you could have more language freedom by basically having fault isolation that's enforced kind of at the thing that you compile into in the object code level. So there's either you can have the virtual machine sort of auto-compiles on the fly, loads and stores that check that you're not out of range and so on. So you can put in software to do all this checking. You can do it at the compiler level. You can do it at the runtime level. The real issue here is it's expensive potentially. And so the question is, what's the trade-off between not having the hardware support and having everything in software versus having the hardware support? Okay? And in many cases, the hardware support is there. There are many who might argue that there are a lot of instances where the software fault isolation is the right thing to do. 601, half a dozen of the other. So, all right. Okay, so let's change topics here. Okay, so we're going to switch gears and talk about caching. So, 61C. Remember that class? Yep, you guys remember the class, I could tell. So the idea of caching is literally like a desk, right? You got all the things you're going to use on your desk, and so they're quick to get at. And you put the things that you need to be actively using on your desk, and in theory, unless maybe you're me, you file things away when you're not using them, okay? Sometimes I manage to do that. So the cache is a repository for copies of things that can be accessed more quickly than the original, all right? And caching underlines a whole bunch of things used today to make computers fast. So we cache memory locations, address translations, pages, file blocks, file names, network routes. All of that stuff is in a cache of somewhere, okay? So if you look, one might joke that all of computer architecture is about caches and maybe a little pipeline stuff. And you could say that all of operating systems is about caches and caches. So, resources, right? So, caching, however, only works well if frequent case is frequent enough and infrequent case is not too expensive, all right? Think about that. You can only cache things well if you put it on the desk and you do that expensive operation, and you can frequently then use the thing on the desk, okay? And the infrequent case, if it's too expensive, it doesn't matter how good your caching is, it's going to blow your time, okay? And there's an important measure, which is this one. Everybody remember this one, probably from 61C, right? Hit rate times hit time plus miss rate times miss time gives you the total time. How do you make that fast? You make that fast by increasing the hit rate as close to 1 as possible, thereby decreasing the rate. Or you can also decrease miss time under some circumstances. So there's lots of ways of making this equation smaller, but certainly keeping the hit rate as high and close to 1 as possible is a good thing. All right, and by the way, of course, hit rate plus miss rate equals 1, right? Right? You remember that whole probability thing, right? The sum of the probabilities equal 1. Good. So why do we bother with caching? Well, in the case of the processor, it's pretty clear. If you look at what happened for quite a while, things were running on, people would loosely call this Moore's Law. It was really Joy's Law, that would effectively double processor speed every 1.5 years for decades, until we got to about 2002. Then it slowed down. If you look at the performance of DRAM, it absolutely didn't keep up. So back in 1980, you didn't need a cache. By the time we got into the 90s and 2000s, if you didn't have a cache, you really were in trouble because your processor was consuming things far faster than your DRAM could hand it to you. Okay? And so this processor memory gap was getting worse exponentially. And so why, if you look at a modern chip, is it got such a large number of transistors devoted to caching? It's because of this. Okay? Basically, performance would be very bad. And the only reason this works is because, well, there's enough locality in your access pattern that caching actually does something useful. Okay? This ringing a bell? So another reason to deal with caching is here's this complicated thing that we've been talking about, and you certainly can't afford to translate on every access. You're going to do a load, so then you first go through the segment descriptors, and then you go through 12 levels of page table, and eventually you got a translation, and then you do the load. Okay? That seems unfortunate, right? Or what if we're using caching to make memory really fast, but now we still got to go through DRAM to translate our page tables? That's really bad, right? So, obviously, we have to cache not just memory reads and writes, but translations, and that's the translation look-aside buffer. One of those names that, in retrospect, is goofy at best, but IBM came up with it so they can name it. It's kind of like you discover a star for the first time, you get to name it. They came up with TLBs, they got to call it, okay? So you get to blame IBM for the name TLB. You still have to remember what it means, though. All right. So why does caching help? You remember locality? Okay, so for instance, if you look at the probability of access, there are these peaks, and so you're likely to access the same thing frequently. So there's two types of locality. Is this ringing a bell, everybody? Starting to remember this, right? Temporal and spatial locality. So temporal locality says if I accessed it now, I'm likely to access it soon. Spatial locality says if I access something, I'm likely to access something close to it in the address space. Okay? And so then we can have many levels of caches. First level, second level, third level, fourth level. Okay, and so the processor might check the first level cache, and if it has a translation, it goes right away. Otherwise, it goes to the lower level, and so on. Starts out at fast first level cache memory, and then fast second level cache, slower second level cache memory on chip, and maybe slightly slower third level cache memory on chip. And then it goes off chip to DRAM, and then maybe it goes to disk. Okay, so this caching kind of expands its way all the way down. And so the memory hierarchy of a modern system looks kind of like this. Registers are like the fastest cache, and then you got a bunch of levels of on-chip, and then off-chip, and then main memory, and then disk, and then tape, which none of you guys have ever heard of tape before. Yeah, IBM with their Scotch tape kind of took over this market. But the idea of this whole hierarchy is you want something that appears to be the size of the biggest thing on the far right with the speed of the thing on the left. And the only way that that works is if you've got good locality. Okay? All right. So there are the Berkeley is famous for many reasons, and another one is the 3 C's. Okay, so remember we talked about BSD, Berkeley Standard Distribution. They also came up with this. So Mark Hill, who's a professor at Wisconsin now, his PhD thesis came up with the 3 reasons for cache misses. The first one was compulsory, which is a miss that happens because you've never touched an item before. That's a compulsory miss. There's no way anybody could have cached it because you've never checked it before. It's also called a cold miss. A capacity miss is one where the cache can't hold all the blocks you're accessing by the program, and so you've kicked a few out. Okay, so my cache is only a megabyte in size, but I've accessed 3 megabytes of data. Well, all of the accesses sort of beyond that first megabyte are going to start leading into capacity misses, okay? Conflict misses are good examples where we have associativity involved. So if you remember associativity, so a direct map, we'll get back to this in just a second, but a direct map cache, for instance, takes a few bits of the address to decide where in the cache it's going to go. And if you loaded it into the cache and then it got kicked out because somebody else wrote over top of it, and then you go look for it again, it's not there, that's a conflict miss. Now, Mark Hill came up with these 3. The fourth one, which I always include, is actually a fourth C. He didn't come up with this one, called a coherence miss. And a coherence miss is an example where you have 2 processors. The first one reads an item into their cache. The second one writes it, which kicks it out of the first processor's cache, and they go to read again, and now it's not there. That's called a coherence miss because it was the write eliminated it. Okay. I'm only going through this really quickly because this is all 61C stuff you totally remember, right? Totally? Totally. Okay, great. C. So how's a block found in the cache? All right, you remember this too, right? So here's the address. Typically, just like with paging, the lowest part of the address in the hardware is called the block offset, and you typically copy that directly or use it directly into your physical, your final address. There's an index, which describes the set, and a tag. So the block is the minimum quantum of caching, just like the offset that we had in a page is sort of the minimum quantum of virtual memory, which is the page. The index is used to look up candidates in the cache, and the tag is used to identify the actual copy. So, did you guys all catch that really quickly? You want me to show you a couple of examples to remind you? I heard a yes. So here's a direct map cache, all right? So, for instance, the uppermost 32 minus n bits are the cache tag, and the lowest m bits are the byte select. And so here's an example of, here's the address. Notice that we have 32 bytes at a time are pulled in out of DRAM. The index here in this case is another 5 bits, so now we have a total of 10, and the remaining bits are all used for the tag. And so typically what happens when you look in the cache is you take the index out of your address, you look it up, that gives you a cache line. You now check and see, does the tag match? And if the tag does match, that's a cache hit. And at that point, you can use the byte select to decide which byte you've got. So that's the example of a hit. An example of a miss would be if that cache tag didn't match, and that's a cache miss, and you have to go to DRAM to pull it in. Okay, now the reason this is called direct map, does anybody want to tell me why is this direct map? Cache? Yes? Every index corresponds to exactly one row. Perfect. All right? So that's direct mapped. And what that means is that if you have 2 addresses that have the same index, which means just that these 5 bytes are the same, 5 bits are the same, they will keep switching each other out of the cache. That'll be a conflict. Okay? Good. Set associative relaxes that a little. So here's a case where this is a 2-way set associative. The index gives you 2 possible cache lines. We check 2 tags, and whichever one is the right one then lets us pull the cache block. So this has got a little less conflict, right? Why? Because if we have 2 addresses with the same index, they can both fit in the cache. If we have 3 with the same index, now we start getting conflicts. Okay? Good? Just reminding everybody? Yeah? Okay? And then finally, fully associative is the most relaxed with no index at all. And all we do is we have a bunch of cache lines, and we look an item up by trying to match fully associatively against the tag, and if we find one that matches, like this one, then we can do the byte select. So I just showed you direct mapped, two-way set associative, and fully associative. Which one is the page table lookup we've been discussing for virtual memory? Is it a direct mapped, a two-way set associative, or a fully associative? Anybody want to take a stab? Yes. So it was a little bit of a trick question. The reason I would say that the virtual memory mapping is fully associative is because there's no limit to which pages can all be entirely mapped in the page table. Because as you see here, I can have any addresses mapped in this fully associative and there'll be no conflicts whatsoever. So the page table is actually kind of fully associative in that sense. All right. Sure. So if you look here, let's back it up to this guy. If you look at this guy, this was the two-way set associative. Notice that these bits here pick two possibilities for storage. So any address that matches these bits, these 4 bits, has only 2 places it could go in the cache. That means only 2 addresses that match in those indexes can be in the cache at the same time. Okay? This guy, it doesn't matter since we have no index, any cache lines can be in the cache at the same time. And the only thing that limits us here is the size of the cache. Okay? Because any cache lines that we happen to put in here can potentially match the cache tag. We don't have any limits. And so there's, any cache lines could be put there. Is that making sense? So what does that mean is, in the case of the page tables we've been talking about, I can pick any pages I want to be given to a process, and there's no limit based on their physical addresses. Got it? Great. And that's going to be important when we get to things like the clock algorithm. Our choices, we do not have to pick pages based on their addresses when we put them into the page table. Okay? Unless we want to for various reasons like page coloring, but that's an advanced thing. So where does the block get placed in the cache? So for instance, we could say if it's direct mapped, and in this instance here where there's 8 cache lines, then for instance block 12 gets placed into the cache in place number 4 here, because 12 mod 8, because there's 8 cache lines, is 4. In the case of set associative, there might be 2 places it could be. In the case of fully associative, it could be anywhere. Okay, and so this is just about how you can use the cache. So in the case of direct mapped, it's the most limited. Multi-way set associative is less limited. Fully associative is the least limit as to which things can go into the cache at the same time. Yes? Well, for some definition of O1, this is also O1 access, because what you do with a physical cache is you build this with hardware matching. And so you don't iterate through it. It's actually done in hardware, where what comes out of this is a bit that says this guy is matched. So the way you do fully associative is not by iterating through. It's because the hardware in parallel checks it. Okay, and if this were 152, which it's not, the thing I would say right now is, that means that this is a lot slower, and therefore going to fully associative is only done carefully. Okay, and so what we'll do is we'll do this kind of fully associative when we do our TLBs next time. Okay, so let's see, what other thing did I want to do before we... So we can decide what we replace on a miss. So when we have a direct mapped and we're about to kick, or we have fully associative and we're about to kick somebody out, or we have two-way associative, we're going to kick somebody out, we can choose who we kick out either randomly or by least recently used. And we can do right through or right back. And I'm actually going to save the discussion of TLB for next time because we're out of time. But hopefully by now you understand that there's many possible page table layouts, and so you want to try to find out what they're like. When you start talking about building something with page tables. We talked about multi-level versions, And we talked about an inverted page table. The difference between forward and inverted: forward page table has a size roughly related to the amount of virtual space in use. Inverted is related to the total amount of physical space in use. So the inverted page table is smaller total. All right, and we'll talk more about caching next time. Have a great Tuesday. We'll see you on Thursday.